20 years. I'm bringing up one example where dark matter in this plot, which is called the diversity problem. Basically, the problem is the observed shape of the galactic rotation curves and the scatter in this plot, which are shown by the dots, is not compatible with what we see in CDM plus baryonic physics. And among different ideas, one possible solution is to have self-interacting dark matter particles. And if we do that, we see with the magenta line here, the scatter, the median plus the scatter of self-interacting dark matter is more easily accommodated into the observed scatter in the galactic rotation curves. So there has been a growing interest toward alternative dark matter models, including self-interacting, in order to address at least some of these problems. And today I'm going to talk about another class of interacting dark matter models, where dark matter scatters off from hypothetical relativistic particles at the early universe, which I call it dark radiation. Oops. Okay. So very similar to dark matter interaction scattering. So dark matter, dark radiation scattering, here's a cartoon of this interaction. So basically, this interaction is effective until the interaction rate falls below the Hubble rate. And the decoupling time scale of dark matter, dark interaction radiation, which is controlled by the particle physics of the specific dark matter model, is encoded into the kinetic decoupling temperature. On cosmological scales, we would see these dark matter models have damped power spectrum with some acoustic peaks, which is very similar in physics, very similar to the baryonic acoustic oscillations. I call it dark acoustic oscillation. That's a name for it. And so basically, it turns out that these dark matter models, if they have similar kinetic decoupling temperature, the shape of the power spectrum is more or less the same, which results in more or less same halo abundance at later cosmological epochs. So for the rest of the talk, I'm taking 3 different benchmark dark matter models in the ETOS project with given kinetic decoupling temperature in the parentheses, and one more example with another kinetic decoupling temperature. I'm coming back to TKD later on in this talk, so it's better to mention it right now. Well, the standard procedure to study astrophysical consequences of any dark matter interaction would be to run n-body simulations. However, n-body simulations are expensive, which makes them improper to study systematically different dark matter scenarios, plus the fact that it has been high priority to push the theoretical prediction toward the lower masses, which makes the numerical simulations even more expensive. And finally, having an analytical model at hand in order to calculate a structure, abundance of dark matter halos and merger rates and merger histories is the backbone of semi-analytical modelings. Upon having a reliable analytical model for calculating the halo mass functions and merger trees, etc., enables us to study the galaxy formation within these dark matter scenarios in much more efficient way compared to the n-body simulations. So the final goal of any analytical model is to give us a detour from the matter power spectrum to the structure, to the abundance of the collapsed halos, which is called halo mass function. Right? This is the first step. Well, so the main candidate would be Pressure formalism, which gives us the number density of collapsed halos if you have the power spectrum and the filter, the window function. However, the exact shape of window function is generally not constrained. You can choose any. So for that purpose, people usually do the calibration of the projector given the dark matter model to the numerical simulation to fix this uncertainty. And upon fixing that, the goal is to have a projector that gives you an accurate prediction for the abundance of the collapsed halos for any given dark matter models, at any given redshift, at any given halo mass, right? So I bring up here one example. I take the simulation results from Ethos projects for CDM and one of the dark matter models, which are shown by like circles and the stars, the error bars. And I calibrate the projector by just having the power spectrum to these simulation results, with solid lines is the analytical Ethos 1, and the dash is the CDM. And it turns out that down to the 10 to the 10 solar mass, where the dark matter, where the numerical simulation data point exists, the agreement is excellent. But the main question remains, with this calibration, with this numerical simulation and the calibration that we have, how well the analytical model does in the lower mass scales. That's where the next generation survey is coming, and we want to test to that mass scales lower than 10 to the 10. So for that purpose, we are running 3 different cosmological simulations for Ethos 1, 2, and 3, with lower box size, but with higher mass resolution in order to probe mass scales 10 to the 8 to 10 to the 10. Still. Okay. So let me pause here for a moment and emphasize on the importance of the choice of the filter. It turns out, again, that for the low mass tail of the halo mass functions from the projector, the choice of the filter is critical. So in this plot, I'm showing you 3 most known filters in the literature: the top hat, the sharp K, and the smooth filter, recently proposed. So basically, on the right plot, I'm showing you the prediction for the analytical model for 2 different filters, the sharp K one and the smooth one. Although in the high mass end, the agreement of these 2 mass functions with the numerical simulations that we ran is good. For the low mass tail, we see the sharp K is doing these oscillatory peaks, which is basically reminiscent of the power spectrum that I used in these plots, while the smooth filter is doing much better job in order to be compatible with the simulations that we carried out. So basically, hereafter, I just take the analytical result that I show is just by taking the smooth filter for the rest of the talk. So in this plot, the calibration for both of these 2 solid lines is the one that I got from calibrating to the Ethos project. So you would see calibrating to the 10 to the, down to the 10 to the 10 solar mass would give us a reasonable fit for a smooth filter, even for 10 to the 8, right? And now the question is, we have the projector calibrated to one dark matter model, one non-CDM dark matter model. How well does it do compared to another dark matter model with different particle physics? So basically, here I show the 3 simulations that we carried out at redshift 0 for Ethos 1, 2, and 3. The data points are the simulations, and the solid line is basically the prediction of the model calibrated to Ethos projects, down to the 10 to the 10. And you see, again, we get more reasonable, more or less reasonable agreement to the simulation results. And also, if we test the model at higher redshift, I took redshift 2, for example. I have tried it with redshift 6 and redshift 10. And still, the agreement to the simulations is acceptable down to the 10 to the 8, where the mass resolution allows us in the simulations. So we have a dark matter model. We have a projector mass function. Sorry. So we have an analytical prescription at hand that enables us to calculate halo mass function in less than a second for any given dark matter model. If you had to run the simulation, probably you had to wait at least a week or so. For the rest of the talk, I'll talk about 2 examples of the application of the model that we developed here. First, I take the estimate of observed number density of galaxies at redshift 6, taken from UV luminosity function measured in this redshift by this paper. And I compare it with the prediction of the models. I exclude halo masses 10 to the 8 or lower than that, because these halos are unlikely to host these observed galaxies due to the photoevaporation caused by background UV luminosity, UV radiation. So we see that these dark matter models with different kinetic decoupling temperature, by the way, kinetic decoupling temperature determines, as I said before, when the dark matter-dark radiation interaction are not effective anymore. So basically when dark matter goes out of thermal baths caused by these dark radiations. So we see different dark matter models with different kinetic decoupling temperatures. The point is, all dark matter models with TKD less than 0.5 are outside of 1 sigma confidence level from the observations, right? And interestingly, this is a similar conclusion reached previously by different authors by combining Lyman alpha forest measurements, CMB, and stellar kinematics to put another constraints on these interacting dark matter models. They reached very similar conclusion, 0.5 keV. And the last plot, as another example and application of our model, I take, again, stellar mass function of observed galaxies at redshift 4 and perform abundance matching to get a stellar mass-halo mass relation for these dark matter models. So this shaded region is basically the stellar mass scales where I extrapolated the Schechter function. And the two main conclusions from this plot would be one, where dark matter models which are consistent with the observations that I showed here, one example, and the other paper that I mentioned, have more or less similar stellar mass-halo mass relation compared to the CDM down to the 10 to the 9 solar masses. And second, the measurement of stellar masses 10 to the 5 to 10 to the 6 is required to differentiate between these dark matter models in the next generation of the surveys. So the future works include continuing working on developing the analytical models in order to study the tidal disruption of substructures within simulations and the semi-analytical modeling. And also study the galaxy formation. I mean, once we developed and completed the formalism, we can use it to implement it into the semi-analytical modeling to study the galaxy formation in these dark matter models. And of course, next generation of the surveys will decide what parameter region in the parameter space of these dark matter models are ruled out or allowed. Thank you.
Okay, let me ask the next speaker to come on up. Go ahead.
Sorry, I cannot hear you. Sure. Mm-hmm.
And so, one thing I think that there's something with it because it matches this shape. But if you actually match that shape, which I think was done in that two photo then that should work. It doesn't end up in the outcome.
So we can talk about this later on, but just to give you an answer. So previous studies shown that, for example, top hat filter doesn't work for warm dark matter models. It creates spurious halos for warm dark matter scenarios. So first we started with the sharp K because in these dark matter models we had the suppression in the matter power spectrum. But then it turns out that the sharp K filter with Schechter, the halo mass function is proportional to the power spectrum. So basically, those acoustic peaks that you see is the direct consequence of the matter power spectrum. We can talk later. We can talk about it later, yeah. Another question?
Okay. I think we're out of time, unfortunately, but
Okay.
thanks for the interesting talk.
Sure.